Okay, thumbs up. Okay, welcome back. So let's continue where we were this morning. So again, we were working towards this new complexity measure. So we're working with space of hypotheses. The hypotheses now map instances to +1, -1. We have a sample. We could have a labeled sample, but actually at this point we don't even care about the labels, just the instances. And we got as far as defining this complexity measure. And eventually what it is that we're trying to do is eventually we want to show something like with high probability for every hypothesis in the space, we want to show that the training error is converging, and we want rates of convergence to the generalization error. Okay, so this is where we were. We're going to use this kind of complexity measure to do it. We're actually going to prove it in a more abstract setting. So we can take this and make it a little bit more abstract, which for the most part just involves changing notation slightly. But first of all, in this new setting, we'll be working with this new abstract setting. We'll be working with functions f. I'm changing notation again just to keep it straight and separate from this, which map from z to the real numbers. Okay, so that's really the only real substantive change, that we're just working with general real valued functions. And they come from some space, capital F. And now we have a sample where the samples come from a space z, so there's z1 through zm. And now we need to modify this definition. So we can largely just formally change the notation. So we'll now measure how well one of these functions matches these labels, sigma I, by this same average that we had before, but now with h replaced by f on the zi's. And then to say how well this entire class fits these random labels, sigma I, we could just take the maximum over functions f in this space. But because these are real valued, the maximum might not exist, so we just have to use supremum. I'm not sure everybody has seen, I have no idea what your background is, to be honest. But supremum just means least upper bound. So whereas it's a lot like maximum, but whereas maximum isn't always defined, supremum always is. Okay, so this is basically just a generalization of maximum. And this will be the complexity measure that we actually work with. And this is called, the notation we'll use is r hat sub f of s. I know it's a lot of notation to refer to the sample that it's on and the space f that we're working with. And this is called the Rademacher complexity. And as we'll see, it's going to be useful for proving convergence bounds. So the kind of thing that we want to prove in this setting is we want a result that says for every function in this class, or with high probability for every function in this class, now what we're looking for is that the empirical average of f, of any function f, should converge to its expected value. So what do I mean by this notation? Well, this is just the usual empirical average on the sample S. And by this I just mean, I guess these arrows mean different things, sorry, equals. By this I just mean the expected value with respect to whatever distribution will eventually be generating the data. Okay, so, and we're going to see in a second that we can prove bounds like this in terms of this Rademacher complexity. So is this okay? Okay. So we're sometimes also going to be interested in the expected value of this. So the expected value of this Rademacher complexity, because you'll notice this is defined on a particular sample, but a lot of times the sample is chosen at random from a distribution, which is going to be the case we care about. And so in that case, the expected value with respect to this random sample, this is going to be denoted by R sub m of f. And they're both referred to as Rademacher complexity. To make it clear, this one is empirical Rademacher complexity, and this one is expected Rademacher complexity. Okay. Okay, so that's the setup. And so here's what we can prove along these lines. Here's the theorem. So let's say that F, the space we're working with, is a family of functions which map Z. And now even though I said we're dealing with real numbers, we're going to assume that the functions we're working with have bounded range. So let's say their range is 0, 1. And then we're going to pick a sample S, like we had before, where each of these Zi's is random, IID, from some distribution D. Okay, so that's the setup. And then what we're going to prove is that with probability at least 1 minus delta, for every function in the class, it's the case that the expected value of f, its true expected value under this distribution D, again using this notation, is at most its empirical average on the sample S, plus, and then here, actually, we can get bounds using either of those Rademacher complexities with a factor of 2. Either the empirical Rademacher complexity, or the expected Rademacher complexity. I'm really messing up. Okay, so either one, you get your pick. It's true for both of them. And plus a lower order term, which is like log 1 over delta over m. Okay, so this term, you can sort of ignore it. It's kind of lower order. And so basically what we're showing is that Rademacher complexity, either one of these, becomes a uniform upper bound on the difference between the true expectation and the empirical average. And eventually what we'll do is we'll plug in things here so that this will be the true error of our hypotheses, and this will be our empirical error, and then we'll get exactly the kind of bound that we're looking for. Okay, yeah?
There's a way to, for given training data, to compute the Rademacher complexity?
Yes, so we'll come back to that. So we're going to see that, I hinted at it before, but I'll hint at it again, that Rademacher complexity is going to subsume all the stuff we did so far. So if you're satisfied with any of that, then you'll like this too.
How does Rademacher complexity change with M?
Well, we'll see. But it's going to end up, okay, it's going to go down with M. So as M gets large, yeah, so M doesn't really show up here, but as M gets larger, it's going to go down. It's typically some constant over square root of M. Okay? Good, yeah.
So you've got R sub F of M.
Yeah,
But on the left you've got R sub M of F.
sorry.
Okay.
Sorry. Okay. Okay, good. Okay, so I would really like to prove this, but we don't have time to fully prove it. But I want to go through the proof and at least give the main steps and the big ideas, because I feel like you should get some idea of how to prove things. If people did the problem set yesterday and that problem too, you know, hopefully if you got through that, it shows you that it's kind of easy to get trapped into giving false proofs in this area. And so I kind of want to show how not to fall into those traps, okay? And so this proof we'll see that. So there are going to be 4 steps, okay? So let's get started. So what is it we're trying to do? We're trying to bound how big this is compared to this. We're trying to bound the expected value of f compared to its empirical average. We want to upper bound that. And we want to upper bound it for all of the functions f, which really means that we want to bound how big the maximum of this is. But again, you can't take maximum, you have to take the supremum. Okay, so this is really what we're trying to upper bound. We're trying to show that the biggest this can be is all this stuff over here. So let's give a name to this. Let me call it phi of s, because it does depend on the sample s. Everything else is fixed. The functions are fixed, function class. The only thing that's random is this sample s. So it's certainly a random variable. So the first step of the proof is, so that we don't have to deal with this as a random variable, is to relate it to its expected value. So the first step is to show that with probability, at least 1 minus delta, probability over the sample s, it's the case that phi of s cannot be much larger than its expected value. It's at most its expected value plus, I'll ignore constants, although they're not hard to fill in, log 1 over delta over m. Okay, this is the claim. How do we prove it? Hoofding is a good guess. Hoofding won't quite work because phi of s is like, it's like this awful, complicated random variable. Yeah, McDiarmid. We can use McDiarmid. So we can't use Hoofding, but we can use McDiarmid. Because in the end, this is really just a function of the sample s. It's a very complicated, awful-looking function, but it's still just a function of the sample s. And so I won't go through the proof, but the proof really is just directly applying McDiarmid. And the main step is showing that if you change one of these zi's in the sample, the most that phi of s can change by is 1 over m. It's just 1 over m. Oh, sorry, this was a typo. Because this empirical average changes by at most 1 over m, so this difference changes by at most 1 over m, and then when you take supremum, it still can only change by that much. Okay, and by the way, this is where this term comes from. Okay? Okay, yeah?
So just kind of a silly question, but like, was McDiarmid's inequality traditionally how people always proved this?
How people what?
All this proved like bounded this supremum.
All the proofs I've ever seen of it do this.
Yeah, because it's like from
Right.
1990, so I was just curious if it was like it just seems really recent.
But I don't know.
Okay.
Yeah. Okay, step 2. Okay. So at this point, oh, I'm sorry. Let me try and be careful with the notation. So I'll try to use subscripts to emphasize what the random thing is. Okay, so this is, here S is the random thing. You know, with the hat means empirical average. Without the hat means that S is the random variable and we're taking expectation. Okay, so this is what we need to work with, this phi of S, right? We would really like to be working with the behavior of this function f on finite samples, on a finite set of points. Just is easier to work with. So this empirical average is already defined on a finite set of points, so that's fine. But this expectation, well, that's an expectation with respect to this distribution D, which is defined over our entire space. Okay, so in a lot of ways, this expectation is a nastier thing to be working with here. We'd rather be working with a finite set of points. So there's a very cool idea that's used not just in this proof, but in other proofs, which is to try to take an expectation like this and replace it by an empirical average. But we can't use empirical average on the sample we already have. So we imagine taking a second sample and taking average on that second imaginary sample. Okay, so we already have a sample S. Actually, I won't bother with these. Okay, we already have this sample S. And now we're going to imagine choosing a second sample. Let me call it S prime. And its elements are Z1 prime, Z2 prime, and so on. And these are also all IID chosen from the same distribution. So everything is IID. They're all from the same distribution. This is the real sample. And this sample is often called the ghost sample. Okay? So the idea then is to take empirical average on this ghost sample and use it as a proxy for this empirical average over here. So again, what it is that we're trying to work with is the expected value of phi of S. Okay, so expected value with respect to S of phi of S. That's what it is we're trying to bound, thanks to step 1. And of course, we can write that out. Of expected value of F minus empirical average of F. Okay, so far I've just copied. Okay, and now the idea is to take this expectation and replace it by an empirical average on S prime, on this ghost sample. Okay, so this now means empirical average on the ghost sample. That's what the S prime means. And then to leave everything else the same. Right, supremum. And now our expected value is not only with respect to S, but it's also with respect to S prime. Okay? That's what we want to do. It turns out, well, of course we have to relate these. You know, it's nice enough to do that, but we have to relate them. It turns out that this expression is an upper bound on this one. Okay, so that's step 2. Step 2 is to prove this inequality. Everybody okay with that? Okay, I even prepared a slide for this, but with great pain, I'm going to skip this because I'm short on time. And also because it's more about like manipulating expectations and stuff, and it's less of a interesting core cool idea. Okay, but just by playing around with expectation, I think I'll give this slide out later so you can read it yourself if you want to. So I'm skipping this proof. Again, it's just manipulating supremums and expectations. And instead, let me move on to the next idea. So when we do this double sample trick idea, there's something else that usually goes along with it. So if you draw IID data, like a sample like this, and then you like permute the data, you mix things around however you want to, the data is still IID. You have not changed the distribution at all, assuming you do the permuting in kind of an oblivious way where you're not actually looking at the values of these random variables. So along with choosing this ghost sample, we can imagine injecting a certain kind of randomness that we can closely control into this entire process. And that does not change the data at all, but it does give us a way of proving stuff, basically, in a word. So we're going to imagine applying just that kind of a process to these two samples. Now that we've drawn these two samples, we're going to imagine going in and looking at each pair and flipping a coin. And if the coin is heads, we'll swap this pair. So we'll take Z1 prime, put it in the real sample, and Z1 and put it in the ghost sample. And if the coin comes up tails, then we'll just leave them alone. And we'll do that for each one of these. So we'll go through one by one, and we'll either swap or won't swap with equal probability. Seems like a weird thing to do, but it's going to, you'll see, it's going to work out. Okay, and again, it introduces randomness that we can control, is what's going on here. So just to write that out, what we're doing is we're imagining a process where we go through these M pairs, okay, and we flip a coin. And if it's heads, then we swap Zi and Zi prime, meaning put Zi in the ghost sample and Zi prime in the real sample. And otherwise, we do nothing. We leave that pair alone. And of course, doing this independently. Okay? And let's call the resulting samples, just to give them a name, let's call those T and T prime. So this will be the new real sample, and this is the new ghost sample. Okay, so what can we say about the distribution of T and T prime compared to S and S prime? They're exactly the same, right? It's exactly the same distribution. We, did all this work for nothing. Okay? But we do get, okay, but, well, let's see what happens. Okay, so let's see. Okay, so we're interested in these differences, right? This empirical average of F compared to empirical average of F on S prime compared to on S. Okay, and now instead we're going to look at the empirical average on T prime compared to empirical average on T. Okay, T and T prime have same distribution as S and S prime. So this difference has exactly the same distribution as this one, as we just argued. We can actually write these out. We can write these out, what these differences are. So this first one is an average of F of Zi prime. Okay, that's this. And then minus, well, here we would get an average of F of Zi, right? But we can just immediately combine those. Okay, so really we get this average minus this average, but I've already combined them into one average. We can do the same type of thing down here. Okay, so we can take this average. And now for each one of these, well, if there was no swap, so Zi and Zi prime stayed the same, then we'll just get the same thing that we had before. This is if no swap for that pair. Otherwise, if they were swapped, then Zi will go into T prime, and Zi prime will go into T. So we'll get the opposite if these were swapped. Right? So we can write this more succinctly as, we could write this as F of Zi prime minus F of Zi, and then multiply either by +1 for this case or -1 for this case. So we could introduce a variable to represent that swap or no swap, and we could call it something like, I don't know, how about sigma I? That seems like a good name. We'll call it sigma I, where sigma I is either +1 for swap, for no swap, or -1 if there was a swap. Okay? So you can see things are starting to look like Rademacher variables. Okay? So just to summarize this, what we've shown, let me call it A, for lack of a better name. So what we've shown is that expression A can be written out as the expected value of S prime. I'll fill in something else here later. So those expectations are coming from here. And then supremum over F in F of this difference, but we can use this difference using T prime and T rather than S prime and S. And in that case, plugging in what we did over there, we'll get 1 over m times sum over I, sigma I. I'm just copying. Okay, just copying that expression. In fact, if you think about it, this is true for any vector of sigmas, right? For any permutation, whether it's fixed or random, it's true, but it's also true if we choose sigma at random in the way that we described. Okay? Are people okay with that step? Yes?
Sigma I equals to 1 is probability 1 over 2, isn't that one just to 0?
No, because of the supremum.
But for any f, isn't it 0?
It will always be at least 0, but not equal to 0. If you got rid of the supremum, then for sure, but yeah. Okay, so that was step 3. Oh, can you turn on the projector, please? I waited too late this time. Okay, step 4. Okay. So let's call this expression B, this expression B. And the last step, step 4, is to show that this expression that I wrote here, B, is at most twice the expected Rademacher complexity. Okay, I messed up the notation. I'm sorry. Okay. Sorry, I messed up the notation. So it's supposed to be R hat sub S of F. And R sub M of F. I mixed up what's the argument and what's the subscript. Sorry about that. Okay, so the last step, step 4, is to show that this expression that we had over here is at most twice the expected Rademacher complexity of F. Okay? And you can see Rademacher complexity is starting to show up here. So let me, hopefully that projector will come on in a second. Whoa. Okay, wasn't expecting that. Okay. Here we go. So here's step 4. I don't know, can you guys dim the lights again? Okay, so here's what we're trying to show, right? That's what I had on the board, exactly that. That's what we want. Okay, so here's the proof. So here's the thing on the left, just a copy of that. So now what we can do is we can just break up that average into these two pieces. So that's just breaking up the average. And for the one on the right, I wrote this as plus, rather than doing minus this average, I did plus, and I moved the minus sign inside here, so you get minus sigma I. And now we can upper bound that by moving the supremum inside. So if you think about it, if you maximize these two terms separately, you get at least what you get if you maximize the whole thing together. Okay, and then we can move the expectation inside. And then you'll notice that this guy only depends on the ghost sample, the Zi primes. It does not depend on the real sample, so the expectation here is irrelevant. And the same thing over here. And now, what is this? This is just that Rademacher complexity, right? Or at least if we didn't have the sigma, it would be Rademacher complexity, right? Just exactly Rademacher complexity. But if we do expected value over the ghost sample, then we get expected Rademacher complexity. And then this one also looks almost like Rademacher complexity, except for the Rademacher variable, rather than sigma I, we have minus sigma I here. But it's the same thing. It doesn't matter, right? We just need a random variable that's +1, -1 with equal probability. So again, that term is also equal to expected Rademacher complexity. Okay, yeah?
You were able to do that because you moved the minus inside, but you also didn't move the minus inside? And would you get something different? I'm just not...
Well, if you had minus an average, yeah, I'm not sure what would happen if you had minus an average then.
Maybe you can't split the supremum up.
Yeah, then you would have trouble splitting the supremum. Okay, other questions? Yeah?
How sharp is the inequality given in the theorem?
How sharp compared to uniform convert? Well, okay, so there are lower bounds that can get proved in terms of Rademacher complexity. I'm not sure how good they are compared to the upper bounds. I can say the constants you get are pretty reasonable, quite reasonable. Okay, so if no more questions, oh, yeah?
How do you get it without averaging over the S rest prime? So earlier you're saying the theorem is also one without averaging over.
Ah, yeah. Okay, so that's the last step. Good. Okay, so I'm all done with the projector now. Okay, so this gives us, unfortunately, I erased the statement of the theorem. But again, the theorem said expected value of f is at most empirical average of f plus, and then there was this additional term which, well, one had expected Rademacher complexity and the other had empirical Rademacher complexity. And then this additional term. Right, so this was the bound that we had. So we've now pretty much completed the proof of this part, except for a couple steps that I skipped. So now how do we go from this to this? Any idea? How do we get this bound? Sorry? Yeah, why are they close? That's right. Well, which bound in particular? Well, we can, this guy is an expected value of this guy, right? This guy, this empirical Rademacher complexity, is a function of the sample S. Everything else is fixed, and this is its expected value. So to show that these two are close, we can again use McDiarmid's inequality. We again just have to make that argument that changing any one sample doesn't change the empirical Rademacher complexity by much. Yeah?
Thing in the lower curly brackets there, is that supposed to be the expected Rademacher complexity?
This one?
Yeah.
No, this?
Okay.
Oh, this is empirical Rademacher complexity, and this is expected Rademacher.
So empirical, you got I think you got the subscript.
Yes, I did. I did. I realized that like halfway through the lecture. Yep, sorry about that. Okay, good. Yep.
So is this saying that the constant in front of the r's is the same in both cases, and so McDiarmid's just gets
Okay,
absorbed
this-
into the O?
This constant actually will be different for these two bounds.
That's
Yeah,
how it
yeah. I'm just folding that into the big O. Yeah, but you get slightly different constants there, yes. Very observant. Okay. Okay, great. Okay. So we proved this bound in terms of Rademacher complexity. Our interest, let's go back to what our interest was. This is it. Enough of this fooling around. Okay. So our interest again is in showing that the training error is getting close to, or what we really want rather, is that the generalization error should be upper bounded by the training error plus something. That's what we want. Well, the training error is just an average of these 0, 1 variables, these indicator variables, as we've seen before. So in terms of the notation before, this is really just empirical average of indicator variables that are 1 if that hypothesis makes a mistake and 0 otherwise. And likewise, generalization error we can write as the probability of a mistake, which is exactly the same as the expected value of these indicator variables. So in applying that general theorem that we had before, what we really want to apply it to are these functions, okay? So we really want to, for any hypothesis H, we want to define a function, let me call it L sub H, which takes as input a pair, x, y, and returns this indicator variable, 1, if that particular hypothesis made a mistake, and 0 otherwise, right? And then we can define the class of all such functions. And so then to get a result like this, like we had up here, what we really want, this is equivalent to saying that the expected value of L sub H for each one of these should be at most, and here this would become the empirical average of each one of these. Okay, so the point is that to get this kind of result, we apply that general theorem that we proved to this class of functions. Okay, this would be the class of functions we apply to, not to H itself. So when we do that, we'll get a bound over here, which is in terms of the Rademacher complexity of L sub H plus the other stuff. Okay, are people okay?
Is that always for 0, 1 loss, or is that a general thing?
This is really general, okay? This is like for any loss. So I'm doing it for 0, 1, but the same thing works for any loss. You really want to apply it to these kind of induced loss functions. Okay, good point. Okay, so, and of course we can also get a bound for expected Rademacher complexity. Let's just talk about this. Okay, so this is maybe not exactly what you want to be working with. You'd rather be working with Rademacher complexity of the hypothesis space itself. But fortunately, this Rademacher complexity can be shown to be equal to just 1/2 the Rademacher complexity of H itself. Okay, so then what we end up with is a bound that says that for all of the hypotheses, its generalization error is at most training error plus empirical Rademacher complexity of H plus something else. Okay? So to get these uniform convergence bounds, the point is that we just have to bound this. Right? So to prove this, that this equals that, I'm asking you to do that as a problem. It's an left as an exercise to the reader. Okay. But we still need to figure out what this Rademacher complexity is. So that's what I want to do next. How do you compute this Rademacher complexity? And how do I fulfill this promise of subsuming everything we've done so far? So as usual, we should start with the easiest case, the simplest case. The simplest case is where the hypothesis space is finite. If the hypothesis space is finite, it turns out that we can bound the empirical Rademacher complexity on a sample S. It turns out that the Rademacher complexity will be at most square root of 2 times log number of hypotheses divided by m. Okay, so we should be happy that yet again log number of hypotheses is showing up in this bound. That's what we expect because that's our favorite complexity measure for finite hypothesis spaces. And when you plug it back in to the bound we had over here, we'll get, aside from constants, we get exactly the same bound that we would have gotten with other techniques that we talked about before, like with union bound. Okay? I'm not going to prove this. I'm not going to ask you to prove it either. Okay, well, that's fine. Well, we already knew how to handle with finite hypothesis spaces. So let's move on to infinite hypothesis spaces. Okay, so one of the beautiful things about this kind of theorem that we proved is that it's in terms of this empirical Rademacher complexity. It's in terms of Rademacher complexity computed on exactly the sample that we received for training. Exactly that same sample, and it doesn't matter what's happening on the rest of the space. So let me write out again what that definition is so we can look at it. So again, it's expected value of this supremum. Since we're working with hypotheses, it could just be the max. Okay, where the xi's are in the sample S itself, right? And again, just to emphasize again this point that it only depends on what's actually happening on the sample itself. So we only care about the behavior of hypotheses in this space on the sample itself. Now, we talked a lot about behaviors of hypotheses on the sample, right? For instance, we had that case with the positive half-lines. And we talked about how the behaviors are things like, all positive, right? We had this kind of example where we listed all the behaviors. And we talked about how you could select one hypothesis for each one of these behaviors. Like here's one hypothesis, H1, that gives all positive. Here's another one, H2, that gives negative and then all positives, and so on. So you could imagine for each one of these different behaviors, choose one representative hypothesis, just one, for each behavior. And we could call that a new hypothesis space. Let's call it H prime. Okay, so H prime means a new hypothesis space where we pick one representative. By a representative, I mean a hypothesis like this from H for each behavior on the sample S itself, Okay, so we're creating a new hypothesis space. A new hypothesis space, right? And it depends on the sample, but that's okay. Now we can ask, what happens if we replace H by H prime here? What will happen? We'll get exactly the same thing, right? Because all that matters is behavior on the sample itself. And whatever realized the maximum here in H, well, there has to be some representative in H prime that realizes exactly that same maximum. So we don't change anything if we replace H by H prime. But when we do that, this new expression is now the empirical Rademacher complexity of H prime rather than H. Well, H might be infinite, in case we're only interested in the case where it's infinite, otherwise we could use this other thing. But H prime is finite. So for H prime, we can use this result over here. Its empirical Rademacher complexity is at most, just plug in over there, 2 log cardinality of H prime divided by M. And cardinality of H prime, well, we have exactly one representative for each one of these behaviors. And the number of behaviors is just the size of the set of all behaviors, right, on that sample S. So this is really just square root of 2 log number of behaviors on S itself, like that effective hypothesis space that we wished we could have used yesterday. So if we take this, and this is in terms of H, not H prime, right? So if we take that and we plug it into our bound, now we get a bound in terms of log of the growth function. It's amazing, isn't it? Oh, God. Okay. How do we get bounds in terms of VC dimension, our last one? Sauer's lemma. We can just use Sauer's lemma, because Sauer's lemma gives us a bound on the growth function, and the growth function is an upper bound on number of behaviors. So if you plug into Sauer's lemma, we'll also get a bound in terms of VC dimension rather than in terms of growth function. Questions? Yeah?
It's the wrong question, but I'm not sure how to. So yesterday,
There are no wrong questions.
the problem said there was something about an open problem where it's not proven or disproven that you can always find a compression scheme. But isn't this sort of a compression scheme that always works?
Pressing to the smaller side of class is for the subset of
Oh, okay, yeah, okay.
Yeah, you want to be, for that one, you want to be compressing down to the samples. Yeah. Don't waste too much time on that problem. That is a really hard problem. I've lost so many weeks of my life to that problem. But I don't know. Some people came along and actually made progress on it, so. Other questions? Okay. Okay, so I guess this brings me to the end of this part of this mini course. So what we've done is we have developed these very general tools for analyzing a learning algorithm, for saying something about performance, based on having a certain amount of data. And so, of course, the point of these results is that when you're faced with a new learning problem, all you have to do is find a learning algorithm that will do a good job of fitting the data while also controlling complexity. And then to analyze it, we just plug into these theorems. Gee, it sounds so easy. Well, it's not that easy, but still these tools are really helpful. So what I want to do tomorrow, and maybe we can just say a few words about it today before we finish up, is to take a look at one particular learning algorithm, which is motivated by a theoretical question. And hopefully we can use it as kind of a case study in terms of how these ideas get used. I'm not sure we'll be able to finish, but we'll see how it goes. So we're going to be looking at an algorithm, but the algorithm actually came from a theoretical question. So let me start by talking just a little bit about that theoretical question. So let's go back to the PAC model. In the PAC model, you remember that we require that for any distribution, the learning algorithm has to be able to come up with a hypothesis with low generalization error. So for any epsilon, if you give this algorithm enough data, it should be able to get error below epsilon. So what if you can't do that? What if you have a learning algorithm which is pretty good? So it's a pretty good learning algorithm. Maybe it can get the error down to, say, 30%, but no matter how much data you give it, it can't get the error down any further than that. So this is kind of a weak learning algorithm, right? It's not a fully strong PAC learning algorithm that can get the error down to 1%, say. But the question is there a way of taking an algorithm like that, which is only pretty good, and converting it into one whose error is as low as you want, below 1%? Or is it the case that in some cases you can do learning part way, but you can't do it the rest of the way? And we can make this problem even more extreme. So what if you have a learning algorithm which does just a little bit better than random guessing? Okay, so if you guess randomly, we're only talking about two-class problems. If you guess entirely at random, you just flip a coin to make predictions, you'll be right exactly 50% of the time. So what if you have an algorithm that's just a little bit better than random guessing? It gets accuracy 51%, error 49%. Can you take that and convert it to one with the error below 1%? Or is it impossible to do that? So we can define two different learning models, or we already have one learning model. One learning model is that standard PAC learning model. In the standard PAC learning model, we have a learning algorithm, or we need to come up with a learning algorithm, and we feed it examples from a distribution D. Okay, so meaning, the xi, yi's, you give it samples distributed according to D, and it outputs a hypothesis H. And our requirement, ignoring this stuff with delta, the requirement was that this hypothesis that gets output should be at most epsilon for all epsilon, all positive epsilon, given enough data, of course, as a function of epsilon. So we might call that strong PAC learning. And now I'm saying, suppose instead that we have a reliable way of getting the error below 1/2 minus gamma, where we're thinking of gamma as some small positive number, like 1%. Okay, for some fixed, like some, just not for all gamma, but for some gamma, we can do that. And we can call that weak PAC learning. And so the question we're asking is, are these two notions of learning the same? Are strong and weak learning equivalent to each other? So if you have a way of weakly learning something, can you also strongly learn it? Or are there some things that you can learn part way, maybe in a weak sense, but not in a strong way? Yeah.
Ensemble of weak learners start to approximate.
Well, good question. So that's the type of algorithm we'll look at tomorrow. Okay. Good. So that's what we'll do tomorrow. Thank you.